Welcome to part 2 of Sound Basics. In this video, we're going to talk about the properties of sound waves. We're going to talk about the amplitude of a wave, the wavelength or its period, the frequency, and phase. So let's start with amplitude. So amplitude is the amount of displacement of air or other mediums molecules. And it tends to be relative to loudness, though we'll talk later on in the series about its relativity. So let's watch this kind of video animation demonstration here.
But if you want another visual representation of the sound, we can hook this speaker up to an oscilloscope and it gives us this graph. We say that this shape represents the sound wave because if we focus on a single molecule of air, we see that it moves back and forth just like a sine or cosine graph. The horizontal axis here represents time, and the vertical axis can be thought of as representing the displacement of that air molecule as it oscillates back and forth. The center line here represents the equilibrium position or undisturbed position of that air molecule. If we turn up the volume, we see that the oscillations become larger and the sound becomes louder. The maximum displacement of the air molecule from its undisturbed position is called the amplitude. Be careful, the amplitude is not the length of the entire displacement. It's only the maximum displacement measured from the equilibrium position.
Right, so a couple things here. First, we're talking about this metaphor that you're probably a little bit more familiar with, this kind of indication of what a sound wave looks like. A lot of times it's displayed as a transverse wave like this, even though it's this sort of oscillation. It's this sort of oscillation back and forth. What we call a longitudinal wave, which you learned by the last time. But as you can see, the longitudinal wave is being represented by this waveform right here, right? So in fact, he talks about the displacement of the molecule, right? But in fact, you can talk about a lot of different ways. Amplitude measures the amount of pressure too. So this might be, if you're talking about one of these peaks, it might be peak pressure or peak compression, and then this one might be peak rarefaction. So that's sort of compression and then opening up. Even though it's visually convenient to think about just the displacement of the air molecules, in fact, what we're really sort of measuring with amplitude is the amount of pressure, right? Amount of compression or rarefaction. The more pressure, of course, the more the air molecules move, and then the louder the sound, okay? The more your eardrum moves when it gets to your eardrum. Right, and so this is representation of it is changes in displacement or changes in pressure, if you want to think about that over time, right? So this is maximum pressure, maximum compression, and this is maximum rarefaction, where the molecules are spread out the most. And then, of course, there's an equilibrium. So this is interesting to see that you're going from high pressure to low pressure to high pressure to low pressure in this sort of oscillation, right? And that's essentially what a sound wave with a pitch has. Now, the more pressure changes from maximum maximum compression to maximum rarefaction. Now that's the amplitude. So the more of it, the louder it is. That's, the higher the amplitude, that means there's more pressure change or more molecule displacement as well. So you can see that here, kind of these animations as well. You can see there's the high pressure and low pressure here, and low pressure, high pressure, low pressure. These are standing waves, which we'll talk a little bit about later, but it kind of shows you an idea of what the sound wave looks like. High pressure, low pressure. Of course, this is normally moving throughout the room. And then you see this particle displacement, right? So this is being displaced that much, particle, but then also these changes in pressure, right? The high pressure and low pressure, the particles are being displaced to the left and then to the right, to the left and to the right. Okay. So that's amplitude, and basically it's one of the properties of sound waves. It's the amount of particle displacement or the amount of change in pressure, and that relates to loudness. Wavelength is the amount of physical space it takes for a sound wave to move through one cycle of compression and rarefaction. So if you think about sounds moving in waves through space, it actually takes a bit of space, right? It has to travel through space a bit of time to get a whole length of compression and rarefaction. Okay, so if you look right here, the wave then now is being compressed, and then it's being spread out, rarefact, and then back to neutral, right? And if we can kind of slow, I don't know, I can't slow this down, but like this whole thing is then one wavelength, right? It goes through a whole cycle of compression and rarefaction. Right. We can look at this one, and this gives a little bit of a, with the static view here. So the wavelength here is, a lot of times they count it from like peak compression to peak compression, right? So the amount of space it takes, the actual amount of space in whatever meters or centimeters or whatever it takes for the wave to go to change from maximum pressure to maximum rarefaction to maximum pressure, that's one wavelength. All right, that's one cycle. And in this other representation, that change over time representation, you go from maximum, and this is, I think, the one that most people are more familiar with, or here we go from complete rarefaction here to compression and back to rarefaction, and then that right there is one wavelength. Okay, so we have an amplitude. Waves have amplitude, sound waves. How much displacement is happening in the air molecules. And then sound waves also have wavelength. So they take up a space. They take up a certain amount of space to go through their cycle. So then one wavelength, if this is, the room, if this is space, one wavelength goes from here to here, right? That's one length of wave. So that's the amount of physical space that it takes to go to travel. One wavelength. Okay. So you can imagine the relationship, which we'll talk about later, between these different things like wavelength, and later on we'll talk about frequency. Okay. So let's move on to the next one, which is period. So period is much like wavelength, except instead of the distance that the wave travels to complete one cycle, which is the wavelength, the period is the amount of time it takes to travel through that whole cycle of compression and rarefaction. Okay? So, and then you can time it then too. So if I take one spot and I go 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, it takes 5 seconds to go from peak compression to peak rarefaction. Again, go try to watch my mouse. It disappeared for a second. So we'll start with the peak compression, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, right there, and then back to peak compression. So that's the period in this slowed down video. It takes 5 seconds for it to go from totally compressed to totally spread out rarefaction back to compressed again to do one wavelength. And then, you can, like we showed before, if you measure from here to here, the space, that's a whole wavelength. And just the period is the amount of time it takes. Okay, so now let's talk about frequency. Frequency, so here I say sound needs time, right? So sound needs a certain amount of time. You can already see that with a period. In order for it to go through a cycle of compression and rarefaction, it does that over a certain amount of time. Now, in order for our hearing, what our brain relies on is a certain repetition of these cycles, right? Not just one wavelength, but a repetition of these wavelengths, okay? And so since it takes a certain amount of time to complete a cycle of compression and rarefaction, to repeat that will take, a certain amount of time. And it happens that pitched sounds, or certain sounds, happen in with some regularity. Even some sort of non-pitched sounds, a lot of sounds that has some element of pitch in it, happens with some regularity, okay? And so the human brain needs a number of these repeated cycles to determine how frequent the cycles repeat. So what the kind of frequency is. And that, again, like I said, relates to our sense of pitch. And I'm sure you know this already, but it's worth saying that the more frequent, or the higher the frequency, the higher the pitch we sense. Okay, that's how we translate the faster moving cycles. It translates to higher pitch, and then the less frequent, or the lower frequencies, translates to lower pitch. All right, so I have a little demonstration here to show you how that works. So if we go ahead and start the super clatter patch, it has this kind of buzzy thing. I'm not going to keep it low in the speakers because I do have to hear it. So right there, you can hear the clicks there happening at about 7 times a second or 5 times a second now, right? And we can hear those distinct clicks. But as we start speeding that up, basically we have a refresh rate in our hearing. And if an event happens and then another event happens at a certain time frame after that event, that's quicker than, like, say 30 milliseconds about, we blend those two happenings, we blend those two events, so then we can't tell the difference. So we start hearing a pitch or a tone, a constant tone, instead of a bunch of different clicks. So if I go up here to 50, you should already have some sense of pitch already, maybe still some sort of sense of click, but certainly when I go to 60 here or 70, it becomes much more tone than pitch, right? And then if I go all the way up to the top, which is 100, it sounds like a tone, and in fact it's happening at 100 hertz. So this is the pitch that's produced at a frequency of 100 hertz. So hertz is cycles per second, or how many cycles, how many repetitions of that wavelength, that period, that cycle happens per second. Okay, and that's what's known as hertz. All right. So generally speaking, for humans have a pitch range of 20 hertz down at the very bottom. Apparently we can hear that. And you have to have some really good headphones or some really good speakers to hear that. And then all the way up to 20,000 hertz. Okay, and that's the limit of hearing. Though very soon after you're born, I don't know how soon, but fairly soon, by the time you're a toddler, by the time you're a young child, you start losing your upper end of hearing. So I'm of a certain age, and really I can't hear much above even like 15,000 hertz, maybe even lower, maybe 13,000 hertz. A lot of the high pitched stuff is already lost to me because of my age. For folks who are a little younger, they'll still be able to hear some of those frequencies, and it depends. Some people maintain their pitch sense for a really long time. Some people can hear beyond 20,000 hertz. So there's a number of YouTube videos, and if you have a good set of speakers and a good set of headphones, you should give it a try and see how high a pitch you can hear or how low pitch you can hear. Give it a shot. Okay, so that there is a frequency, and I demonstrated that. And then let's talk. Let's just have this to hear about sound waves in different media. So basically, frequency depends on the air pressure, right? And also the density of air. So because it's traveling through air, which is essentially a gas, and it has a certain density. And so the sound waves are gonna travel through air at a certain speed, right? Now, if you change that medium, as we'll see in this video, you change the frequency. So for example, in helium, sound moves much faster. So similar sounds sound much more high pitched because they travel much faster through the medium helium. And I forget what the carbon hexafluoride or something like that, a denser gas, sound a lot lower pitch. So let's check this out.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
The simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that,
and my voice gets really low, although somehow I'm still funny. It's scientific!
All right. Thanks, Mythbusters. All right. Now, finally, let's discuss phase. Okay, so phase really is a characteristic, kind of a characteristic or property of sound, maybe more of a characteristic, I mean to say. All right, so let's look at this unit circle. Now, a pure tone that you hear, that we use a lot of in experiments and teaching and stuff like that, is basically follows a sinusoidal pattern. And what I mean to say is that it's cycles of compression and rarefaction. Okay, how it moves from neutral air pressure towards maximum air pressure, back down to minimum air pressure, much more less pressure. Okay, if it happens in this sort of sinusoidal way, you get a very pure tone. Okay, I hope that makes sense. If the change happens, so remember this representation is in the actual wave. We're looking at change over time. So if it starts getting more and more pressure over time, and then less and less pressure over time in this sort of fashion, that follows a sine curve, then it's a pure tone. All right. So basically, it follows this unit circle. So you can trace the unit circle, and you can see how that happens. I'll just play the video. You can see how it happens as you're moving x to y, right, over time. Time is moving along. You go to maximum pressure, and then if you just follow the circle along, you go to minimum pressure, and this is the change in pressure here. That's the maximum pressure, and then minimum pressure back again, right? Now, then you could talk about where you are in the cycle in terms of the unit circle, or either degrees or radians if you want. So basically, you can talk about, I got to do it here. You can talk about, if I go to 45 degrees, this is where I'll be in the cycle. This is where I'll be in the amount of pressure change. If I go to 90 degrees, that's where I'll be, maximum pressure, right? If I go to 180 degrees, I'm back to neutral, right? So if I start at here, so again, you can just talk about in terms of this unit circle, the sinusoidal wave, this change over time, okay? And it doesn't. This is a good way to think about it, and it's not necessarily this clean for every sound, but again, these pure tones is a good way to think about this change. So you could talk about, like for example, we will talk about later, especially when we're talking about spatial sound, in terms of like initial phase, a certain sound or certain element of sound starts maybe here instead of there, or starts maybe here instead of there. And why is this important? Well, later on, we're going to talk about constructive and destructive interference, how sound waves combine to eliminate each other or combine to emphasize each other. So for example, a good example is noise canceling headphones. Basically, there's a little microphone on the headphone, and it listens to all the environmental sound, and then flips them, what we would say, it flips them 180 degrees out of phase, right? And then pumps that information through the headphones back to you. So basically, it cancels out all that environmental noise. So that's how noise canceling headphones work, okay? And what do I mean by that? So if you take maximum pressure, for example, okay, which is right there, right? Up here, maximum pressure, we're at 90 degrees, right? And if we go 180 more degrees, right? Where are we? Let's see. If we go 180 more degrees, so we're down here now, right? You notice it's maximum rarefaction, right? So this added to that becomes zero. It just cancels each other out. So that's essentially what happens in a lot of these sort of canceling things. And for example, recording, you can get phase issues where you have the same signal, but they're slightly out of phase. So some weird things are happening, or they're a lot out of phase and they start canceling each other out considerably. We'll talk about that a little bit more later, but that's an important quality of sound. It doesn't actually, it's kind of not an active property like frequency is, but it's an important thing to think about in terms of sound waves, is like what actual phase it is in comparison. Really, it's kind of a relative thing in comparison to what other sound is going on in their phases. Okay, so that's pretty much wraps up part 2. We talked about the properties of sound waves, talked about amplitude, which is the amount of sort of displacement of that molecule, or that actually really represents a change in pressure, the amount of change in pressure. The wavelength and the period that these sound waves travel through space, and it takes a bunch of time, it takes some time to travel through space. So the length of one cycle is the wavelength, how much physical space it takes for the pressure waves to travel to complete one cycle. And the period is the amount of time it takes for it to go through one complete cycle of rarefaction and compression. The frequency is now, with these repeated cycles, if these waves continue to repeat, it's how often they repeat and at what what speed or what kind of frequency, what click it repeats at, right? So the higher frequency we talked about, in any kind of any kind of regularly periodic repeating sound wave has a pitch, and the higher frequencies have higher pitches and the lower frequencies have lower pitches. And then we talked about phase, which is this kind of like conditioner, or rather than a property, it's kind of an element of sound. It's where you are in the cycle, really, and that could be important when you're talking about different sound waves being relative to each other. Depending on where they are in the cycle, they can add together or cancel each other out. Okay, so I hope that was helpful. Join us for part 3 when we talk about transducers, meaning like speakers and microphones in the ear and how they work.